Hello, Calculus 2 students. Today, parametric curves. Essentially what we're going to be learning today is how to parameterize curves in 2 space. If you had some sort of curve that at different points in time were at a different location x and y. Now notice that what I've drawn here does not pass the vertical line test or the horizontal line test. We don't need to worry about y being a function of x or x being a function of y, but we do want x and y to be functions of a third variable, which we'll assume is t for time. As time goes on, x and y take on different values. You get a point moving around on the xy plane essentially. Now we do want x and y to be functions of time, meaning that at any one time we don't want to have multiple points being drawn at the same time. If I say time, then I'm just talking about t, but t doesn't necessarily have to represent time, but it's a good way to think about this so you can imagine points moving as time elapses. We're going to let time vary between -1 and 2. To help us with this, we're going to make a table from -1 to 2, so let's just do the integers. Plug these t's into the x function right here, and you get different x coordinates at different times. We get 5 as the x coordinate when time is -1, and now let's plug in that same time into the second function. We get 2. So we can already start making a graph here. At time -1, this graph starts at the point 5, 2. Times 0, plug in 0 for the t's, we get 3 for x, 1 for y. So we wind up at this point at time 0. Then at time 1, we get 1 for x and 2 for y. Plug in 2, and we get -1 for x, 5 for y. Now, this is only 4 data points. We could say, hey, what happens at time 0.1, 0.2, 0.3, 0.4? You'll get a lot more data in here and plot a lot more points. Or we can just understand what's happening as time increases. T is increasing, so 3 minus 2 times t will be getting smaller. The x coordinates started at 5 and they finished at -1. Whereas the y coordinates had a dipping effect. They started at 2, they dipped down to 1 and went back to 2 and then up to 5. If I had done other points, I would have seen something like this happening, where the x's would have decreased while the y's dipped, and then the x's continued to decrease while the y coordinates go back up again. And so this would appear to be the path of the point as time varies from -1 to 2. Now we're going to confirm this with technology, and over here you're seeing the syntax that you would type in to do an animation. And I have this already open in a Desmos tab. The only difference is I'm going to use a capital X and a capital Y for my x and y functions. When you first type these things in, it's going to make a graph. Now what this is doing, it's graphing you the function, essentially y equals 3 minus 2x. Desmos is programmed to treat t as the input variable, so it's going to make the horizontal axis be t, and the vertical axis be the output of this function, which is x. That might feel weird, but normally we're so used to thinking the vertical axis to be interpreted as a y coordinate. The horizontal axis in this red graph that we're looking at right now is t, and the vertical axis is x. In this graph, the horizontal axis is t, and the vertical axis is y. Now, I don't really care to see either of these graphs. What I really am interested in seeing is what happens when you put them together and form a ordered pair. So I'm going to put the x of t in the x coordinate position and the y of t in the y coordinate position in that third line there. Now, if I change this capital T right here, you see there to a 2, and then reveal this graph, this is showing us what we just did by hand. Little t varies between -1 and 2. Now, if you want to create an animation, that's what the next 2 lines are about. Change the right limit from a 2 to a capital T. Then Desmos will say, hey, do you want to create a slider? And you say yes, and so it creates this line down here. For capital T, you put the actual limits on time, so -1 to 2, and step size of 0.01. That way, when you play the slider, you can see the graph actually animate as time goes from -1 to +2. If you also want to see the point, then make this one right here, but instead of little t's, put capital T's in there. So what this is going to be doing, I'm going to reveal that point. This is saying, hey, when capital T is whatever it is, in this case I parked it at 0.73, it's going to plug capital T into the x and y functions and get an actual point and then plot that point. This reveals the point, and if you want to erase the path, then you can just see a point moving. Alright, you're going to want to get pretty comfortable typing this kind of stuff into Desmos so that you can animate a lot of things, and it helps gain an understanding of what's going on and what we're trying to accomplish. Sometimes you're expected to make a graph of the point as it moves around when you're only given the images of x against t and y against t. And you can make a table just like you did before, except we're going to use the images to get our outputs. Time from -1 to 2, so let's just focus on that interval. So then you look over here at this graph of x against t, and then you say, okay, when time is -1, what's the output of this function? You can see way up here at the point 5. So the x coordinate is to be interpreted as being 5 when the time is -1. When the time is 0, the output's 3. So the x coordinate will be 3 when time is 0. Time 1, it looks like the x coordinate's 1, and at time 2, the x coordinate is -1. Now we're going to focus on the y against t graph. So when time is -1, the output of this function is 2. So y will be 2 when t is -1. T is 0, y is 1. When t is 1, y is 2 again. And when t is 2, y is increased to 5. Then we go to this graph, and this is y against x. We're at the point 5,2 when time is equal to -1. We're at the point 3,1 when time is 0. We get to the point 1,2 when time is +1. And we finish at -1,5 when time is 2. And then we have the same graph we had before. These little arrows just indicate the direction at which the curve is drawn as time advances. The next thing is about eliminating the parameter. The parameter is the variable t, by the way. And what I want to do is I want to actually come up with an xy equation that makes the same image. So we can, in a sense, know what the path is going to be ahead of time. And by this same image, I'm referring to this parabola over here. If I can predict the path by eliminating the parameter and going back to just x's and y's. In general, you can say, okay, well, x is equal to 3 minus 2t. Take this equation and solve it for t. And I get that t has to be 3 minus x over 2. And then I go to the second equation and I replace this t with this expression. And we have 1 plus, and then replace the t with 3 minus x all over 2, and that's being squared. What I've just done by doing this is I've created an equation that is independent of time now. This is just your basic relationship x against y. Let's go to Desmos and type this in. There's no time in this picture. It's just x against y. You can think as x changes, y changes. But this will predict the path. If I reveal the point and then animate it, it follows this parabola as time varies from -1 to 2. Now, in this window of time, of course, we don't draw this entire black parabola. We only draw a portion of it. When time gets there, we only have this much of it. This is referred to as a Cartesian equation. When I use the word Cartesian, it means that we're talking about x is a horizontal followed by y, which is a vertical. And of course, when we graphed it, there's a parabola that went through the points that we expected it to go through. Parameterizing curve. Find a parameterization of the curve given by the equation below. So here's a Cartesian equation, no time involved. We want the parameterization to begin at the point 3,1 when time is 0, and end at the point 7,5 when time is 6. So we're going to draw a different portion of this, and it's going to go in a different direction. All right, so we want time 0 to be starting there, and here we want this to be when time is 6. This is the direction it's being drawn. So the table of points, we want this to satisfy. So at time 0, we want x to be 3 and y to be 1. And by the time time gets to 6, we want x to have increased from 3 to 7, and y will have increased from 1 to 5. All right, what we're going to do is we're actually going to focus on making sure that x turned out correctly. We'll say determine x of t first. You can do a visual of this if you'd like. You can create a t against x graph. X is now the vertical axis and t is the horizontal axis. At time 0, we want x to be 3, and at time 6, we want x to be 7. So I want to find a function that connects these dots, and I want x to increase from 3 to 7 as time increases. There's lots of ways you could do this. You can come up with pretty much any curve you want that connects these, where x is getting bigger as t is getting bigger. But the most straightforward way is just to find a linear one, to go straight from this point to that point. Okay, so we want to find the slope. We rised from 3 to 7, so the rise is 4. And we did that as t increased from 0 to 6. So the run was 6. We get a 2/3 slope here. The vertical intercept is 3. So it should be that x of t equals 2/3 of t plus 3. Once you've figured out that part, then finding out the y is actually rather easy. You go back to the given relationship that's right here, and you simply substitute. You change the x to this expression, and then all of a sudden you have a parameterization for y. Therefore, y as a function of t. It's 1 plus a quarter of 3 minus, and then replace that x with 2/3 of t plus 3. This negative will distribute these parentheses, so the 3's will cancel, and we'll just get 2/3 of t inside there, and that's being squared. And I might as well square that. It's going to become 4/9 of t squared, which means that 4/9 times a quarter is 1/9. So when all the simplifying is done, you should just wind up getting this 1 plus 1/9 of t squared. Put our two functions side by side. Also specify our interval. Time is in the interval from 0 to 6. And this should accomplish our objective. Let's test it. We have to change this left endpoint. I don't want to go from -1 to 2. I want to go from 0 to 6. So make that 0, but leave that capital T, and then change your capital T window from 0 to 6. Start at 0 now, hit play, and you can see at time 0, it started at 3,1, and by the time we got to time 6, we were at the point 7,5. Still part of this overall parabola. So here's the same curve, but do a different parameterization of it. Find a parameterization of the curve given by the equation below. The parameterization should begin at 0.75 when t is 0. go to and turn around at the point -1, 5 when t is 1. So we want it to travel pretty quickly, like in 1 unit of time, and get to right here. But then we want it to turn around and then go back, riding along the same arch. By the time we get to time 2, we want it to finish where it started. Let's start by doing a small table of points. Time 0, we want x to be 7 and y to be 5. At time 1, we want x to have decreased to -1, and y is going to actually still be at 5 at that time. And by the time t gets to 2, we want x to have returned to 7, which means y will still be 5. And again, we're really just going to focus on making sure that x will go from 7 to -1 back to 7. And then once I figure out that relationship, the last column will happen automatically if I plug that x relationship into right here. Now, there are lots of ways that you can do this. There is no one right answer here. Let's go ahead and get a visual of x against t to help us in our quest. At time 0, we want x to be 7. And when time is 1, we want x to be -1. The axes are not to scale to each other. And by the time time gets to 2, I want x to return to height 7. Now, as time goes on, I want x to go from 7 down to -1. We need to do some sort of graph that goes from this point to that point, but then in the next second, it goes back up to that one. Pretty much any curve or any shape that you can come up with that does something like this will accomplish our goal. You can make it a V, a line segment followed by a line segment, or you can do a parabola. There's lots of different ways you can do this. Let's do the parabola. Let me move some things around in my work here. Okay, so your basic parabolic function, x is the output, is just t squared. We're going to do transformations of this until it looks like the parabola we see in this image. We're going to shift it to the right 1. To shift right 1, you replace t with t minus 1. Then we want to shift down 1. To make it go down 1, put a -1 after. And let's not put x of t here because I want only x of t to refer to our final answer. The next thing is we got to make sure that the parabola is narrow enough or wide enough so that it goes through 0, 7. The way to control that is to put a unknown scale factor in front of here, where we're going to have to determine what that scale factor is. Now all we have to do is just figure out what a is so that we get the correct outputs. And because parabolas are symmetric, I only have to test one of these outputs and the other one should happen automatically. So I want to get 7 when I plug in time 0. We just got to figure out what a is to make this true. We get a has to be 8. So we have in the end, okay, now we have to figure out what y is going to be. Take this expression and you plug it in for that x right there. And so we get y as a function of t is equal to 1 plus a quarter times parentheses 3 minus, and then all of this goes in for x. So we've got to use some more parentheses. 8 times more parentheses, t minus 1 squared minus 1, n parentheses squared. Now, if you'd like, you could do some simplifying here. I'm not going to worry about simplifying this too much. Let's just go maybe one extra step and we'll call it good. But you could take it further. I'm going to distribute this negative so I get a plus 1 over there. So that just becomes a 4 and then minus an 8 times t minus 1 squared and parentheses and then square again. This will be good enough. We're going to type that in next. Okay, let's reveal the Cartesian graph and let's adjust our times. We want this to go from 0 to 2 this time. Well, 0, the left endpoint's good. Keep that right endpoint t here, but down on the t interval, change this 0 to 2. And then let's reveal the point. So at time 0, we are in fact at 7, 5. And then as time increases, by the time we get to time 1, we get to -1, 5. And then by the time we go back to time 2, it's returned along the same path back to where we started. Find a parameterization that forever oscillates between the point 7, 5 and the point 3, 1. Okay, so we're going to focus again on just the x-coordinates. Notice it doesn't say where it has to start or end or how much time it takes. We just want it to go back and forth forever between these 2 points, which means that we want x to oscillate between 3 and 7. So our goal will be find the x function such that it oscillates between 3 and 7. The graph of x against t, here's 3, here's 7. I want something that just goes back and forth between 3 and 7 as time goes on. So I think I'm just going to use a sine wave or a cosine wave. You can pick one of them. And I'm going to shift it appropriately, get the amplitude right so that it oscillates between 3 and 7. Let's start with a sine wave. First thing I want to do is get the amplitude right. So if you're bouncing around between 3 and 7, you got to figure out where the center of that is. 3 and 7 are 4 units apart, so 5 will be that location. So our amplitude of our wave is going to be 2, which means you need to double the sine wave. And then we need to shift it up 5. And here I've just created a function, x of t, that will oscillate between 3 and 7. And then the y of t is going to be equal to 1 plus a quarter, 3 minus, and then put this x function in parentheses next to that. All of that now will be squared. And we'll do a little bit of simplifying here on this one. We'll distribute this negative across. That's going to become a -5, and 3 minus 5 is -2. You could factor a -2 out of this and then square that. Now let's go ahead and do that. Why not? This is going to simplify even nicer. I'm going to factor a -2 out. That leaves a 1 plus sine t. This -2 that I factored out also has to be squared. And that's going to make a 4, which is going to cancel that 1/4. So it looks like 1 plus and then 1 plus sine of t, and that's being squared. So I'm going to type this in for the x and this in for the y. Okay, on this one here, let's go ahead and just start it at time 0. It doesn't really matter where we start. Let's go up to time capital T, but let's let capital T be something large so we can see what happens as time just goes on and on. Let's make this be 20. And I think I'm ready to hit play, right? As time goes on, this curve just oscillates forever between the 2 points we wanted along this parabola. This slide here is encouraging you to explore, to type these different things in. I don't think I'm going to take the time to do all this in this video. All the bottom ones are circles, 4 through 9, and there's some things we learned there with circles that are going to be important. Let's just do some of these, but I encourage you to type all of these in, change your time intervals, and just see what happens as time plays. Let's do number 2. So x is sine 12t, y is cosine of 10t. Now, this is going to be a fun one to watch what happens as it draws itself. You can definitely see it not repeating its path up to a certain point. By the time we get to time pi, the point has moved onto its path again. We get a very interesting symbol that's produced and then redrawn as time continues. Lots of strange things will happen when you just mess with these things. Let's make that just a sine 2t, see what this does. Sine 3t. Let's go to 4. Negative sine t cosine t from 0 to pi. As time varies from 0 to 2 pi, notice what is happening here. Looks like we're getting a circle, centered at the origin, radius 1. It starts at the top of the circle, and it draws itself counterclockwise. And by the time we get to 2 pi, it's finished one full circular path. Let's look at 5. It's going to be different about 5. I'm going to switch the sine and cosine, that's it. So x will be negative cosine, and y will be positive sine. All right, this time we're getting a circle that starts at the left side and draws itself clockwise, completing itself by the time we get to time 2 pi. Number 6, 3 sine t, negative 3 cosine t. Okay, so we get a circle again, just a bigger circle. But this time starting at the bottom, drawing itself counterclockwise, and by the time we get to 2 pi, it's done one rotation. Number 7, let's make x be cosine, y be sine, but both positive, and 2 t's. Here's our circle that's starting at the right, going counterclockwise this time. It draws itself once by the time t gets to pi, and then draws itself again by the time t gets to 2 pi. Any guesses what's going to happen if I make those 3's instead? Make them both 3's, that is, not just one of them. 1, 2, 3. Draw itself 3 times by the time time gets to 2 pi. If I keep x and y be sine and cosine, and it looks like changing the coefficients will tell you how many rotations it's going to do in a 2 pi interval. And if I make one of them negative, it's still drawing itself 3 times, but it's a different direction, and it started at a different point. So you're starting to see that we have some control over where I start the curve and which direction it's going to go and how many times it gets drawn in a 2 pi interval. And then let's do number 9. Let's first type in just cosine t, negative sine t. This is going to draw itself once. It's going to start at the right and go clockwise. What happens if I put a 2 plus in front of that? Adding 2 to the x function shifted the circle to the right too. You can suspect what's going to happen if I add a 3 to this one. So we have the ability now to not only make circles centered at the origin, but we can move the center to other locations. Find a parameterization of the circle below that meets the following criteria. Then eliminate the parameter to find the Cartesian equation of the circle. At time 0, we want to be at the left side. We want it to go clockwise. We want it to finish by the time we get to 4 pi, which means that it's over here by the time half that interval. It's up here when time is pi, and it's down here when time is 3 pi. We want this to draw itself clockwise, not counterclockwise. One way to switch that is to mess with negatives. I just throw a negative in front of the y, and this is making it go clockwise. But it's not starting at the right spot. Okay, let's pause the animation. The way it's currently written, plug in time 0, you get x equals 1 and y equals 0. So that means that the starting point is at 1, 0, which is the right side of the circle. I want it to start the left side of the circle. So I'm actually going to put a negative up here. Bingo. So it starts at the left side, and it's going clockwise. If I'd also put a negative sign in front of here, this would have had it go counterclockwise. Now the radius is wrong. To fix the radius, we just got to change the amplitudes of these waves. So double both, and this creates a new radius. Now the other issue is that this is drawing itself too quickly. It's finishing by the time we get to 2 pi. I want this to draw half of a circle by the time we get to 2 pi. So that tells me we should put halves in front of these t's. And now let's change our capital T window to go up to 4 pi so we can see the whole thing. And we've accomplished it all. I got the right starting spot, I got the right direction, I got the right radius, and I got it drawing itself once over the interval from 0 to 4 pi. Okay, so we found that x was equal to negative 2 cosine of 1/2 of t, and y was positive 2 times the sine of 1/2 of t. To make sure that you're drawing circles, the coefficients should always be the same, and the coefficients of the t's should always be the same. Otherwise, you're going to get non-circles. The coefficients here give you the radius, and the coefficients here tell you how much of the circle will be drawn if you go from 0 to 2 pi. Okay, now we need to eliminate the parameter to figure out the Cartesian equation for this circle. Notice that if I were to take x, whatever it is, and square it, and then take y, whatever it is, and square it, in this particular case anyway, we would get, we're going to add to that y squared, then we can factor out the 4. Whenever you have cosine squared of theta plus sine squared of theta, as long as those thetas are the same, then the Pythagorean theorem kicks in and this is going to be equal to 1. So in the end, this is just 4. So in Cartesian coordinates, notice this is a slightly different approach than what we did last time to eliminate the parameter. When you know you're working with a circle, this is the way I recommend. Leverage the Pythagorean theorem, and this is your standard form for a circle that's centered at the origin whose radius is 2. And here's another one. Let's not worry about the centered part first. The point is at the bottom of the circle at time 0. The point revolves around the circle counterclockwise, and by the time time gets to pi, it's back to where it started. Time pi halves, we want it to be up here. Time pi quarters, we want it to be over here. And time 3 pi quarters, we want it to be over here. Let's get the rotation and the starting spot correct, and then we'll worry about the radius. We'll shift the center last. Okay, so this is drawing itself starting at the right. It's going the right direction. It's going counterclockwise. We want to start at the bottom, which means I need to switch the sine-cosine assignment. But this one's starting at the top. I want mine to start at the bottom. So I want the initial y-coordinate to be -1, not +1. That tells me to throw a negative in front of that cosine. And that automatically also fixed the orientation. It's going counterclockwise. If we wanted clockwise, then I would also put a negative in front of the sine, but that's not what we want. We want this one. Now we want it to draw itself once by the time we get to pi. Right now it's drawing itself once by the time we get to 2 pi as our time. So we need this to draw 2 complete circles by the time it gets to 2 pi. So put 2's in front of these t's. And this makes it so that in the interval from 0 to pi, it draws itself once. So let me change my capital T so we just end at pi. T0 to t pi draws itself once. The radius we want to be 1. Well, it's already 1 because the coefficients of sine and cosine are 1, so we don't have to change that. The final thing is we want the center to be right. Move the graph right 1 and down 2. So if we add 1 to the x function and remove 2 from the y function, that'll get our center down to the point 1 comma -2. And our equations were, we wanted the x-coordinate to have sine, we wanted a radius of 1, we wanted to draw itself twice in a 2 pi interval, so put a 2 there. We wanted the center shifted to the right 1. Y had to be negative cosine of 2t and then shifted down 2. Alright, in this one here, we want to now find the Cartesian equation of this circle. This circle's been recentered. What I'm actually going to do is I'm going to take these equations I got here, and I'm going to get it so that the sine and cosine are alone on one side. So the +1 and the -2, I'm going to put back and join the x and y. I'm going to square x minus 1 and square y plus 2. Square that sine, we have just sine squared of 2t, and then plus, and now we're going to square this. That square is going to make that negative go positive, and then we'll have a cosine squared. And the Pythagorean identity kicks in, and this is just equal to 1. So here's our Cartesian equation. Notice this is what you're used to seeing with regards to a circle whose radius is 1, but whose center is at the point 1 comma -2. This is a fun section. Enjoy.